Hey everybody, we're beginning a new chapter, a new module, and this is called graph theory. Don't let the name fool you. In this module, module 13, graphs, we are not considering graphs in the sense of graphs of functions, graphs of equations, graphs of lines, and I can add to that graphs. Oh, maybe I should have left well enough alone, but here I go. Or graphs in the XY plane. So in this module, module 13, a graph is not a graph in the traditional or conventional sense. So we're not talking about graphs of functions. We're not talking about graphs of equations. We're not talking about graphs of lines. And we're not talking about graphs in the XY plane. What are we talking about? Well, let's start with a simple definition. In the context of Module 13, a graph is a set of points called vertices, and the singular is vertex. So if we have more than one vertex, we call them vertices. A graph is a set of points called vertices together with a set of line segments or curves called edges. And each edge must begin and end at a vertex, not necessarily the same vertex. I'll tell you what, let me erase the board from here up, and we'll draw some pictures and examples that illustrate the idea of graph in our present context. Here's an example. We have a point V1 and a point V2. They're two distinct points, and there's an edge, E1, that joins vertex V1 and vertex V2. We could also draw this same graph using literal points and label the vertices this way, V1, V2, and we'll label the edge E1. So here's a graph, V1, V2, and the edge connecting them is E1. The graph consists of a set of vertices and a set of edges. So the set of vertices together with the set of edges forms our graph. You know what? Sometimes I may represent a graph this way, sometimes I'll represent it this way. But I think most of the time I'll represent it this way. Let's look at some more examples. Here's an interesting example. We have one point, a vertex V sub 1, and we have one edge that begins and ends at the vertex V1. That's perfectly legitimate. That's allowable. Here's our vertex set. Our set of vertices is V1, and our set of edges is E1. The set of vertices together with the set of edges forms a graph. This is a graph. And there's something interesting about this particular graph. It has one edge, and that edge starts and ends at the same vertex. Whoops. The edge E1 starts at vertex V1 and it ends at vertex V1. It starts and ends at the same vertex. Edge E1 starts and ends at the same vertex. So we call E1 a loop. And I'll define that formally in just a minute. We'll make this formal. Here's our definition. An edge E is a loop exactly when it begins and ends at the same vertex. So if an edge starts at a vertex and comes back and ends at that vertex, it's a loop. Now let's look at some more examples of graphs. Here's a rather complicated looking graph. We have 5 vertices, V1, V2, V3, V4, V5, and a whole bunch of edges. E1 goes from V1 to V2, E2 goes from V2 to V3, E3 goes from V3 to V4, E4 goes from V4 back to E1, edge E5 goes from V1 to V5, edge E6 goes from V5 to V4, edge E7 goes from edge V5 to V3, and edge E8 goes from V5 to V2. So these 5 vertices, V1, V2, V3, V4, V5, together with all of these 8 edges, the set of vertices and the set of edges forms this graph. Now, graphs have an interesting historical significance, and believe it or not, they're extremely useful today, especially in the computer age. Our text has a historical background about graphs called the Kernigsberg bridge problem. And you might want to look at that. It's a pretty interesting problem. I'll give you another historical example of a graph. This one probably not as old, but it's fairly old, but not old enough to precede the era of electricity going from power plant to houses. Here's a classic problem. Given 3 utilities, gas, water, and electricity, and 3 residences, we'll call them 1, 2, and 3. Is it possible for each of the 3 utilities to serve each of the residence customers with a direct line without the lines crossing? Customers, residences. This problem's been around, well, let's see, I knew about it when I was 10 or 11 years old, and it was not a new problem then. So, I don't know if it's been around 100 years or not, but certainly 80 or 90, I would say. Let's see how we can do this. We'll take gas and go to residence 1, and we'll take gas and go to residence 2, and we'll take gas and go to residence 3. No problem there. The gas company serves all 3 residents with a direct line. And we want water to go to residence 3. And we want water to go to residence 2. Looks good. Whoops. And we want water to go to residence 1. You know what? I think we can do a little better. I'll tell you what. Let's have this water line going from water to residence 1, and then we can have another water line going to residence 2, and we have water serving all 3 residences. And let's see how I can denote this. Here, I'm going to start a convention where I denote an edge by the name of the vertex at which it starts and the vertex at which it ends. So vertices, we go from gas to 1, we'll call that G1. We go from gas to residence 2, we'll call that G2. We got gas going to residence 3, we'll call that G3. And we got water going to residence 1, we'll call that W1. We have water going to residence 2, we'll call that W2. These are the names, I'm sorry. I am so sorry. These are the names of the edges. I'm going to start the convention of naming edges by naming the vertices at each end. G1 goes from Vertex Gas Company to Vertex Resident 1. G2 goes from Vertex Gas Company to Vertex Resident 2. G3 goes from Vertex Gas Company to Resident 3. W1 goes from Vertex Water Company to Resident 1. W2 goes from Vertex W Water Company to Vertex 2 Resident 2. And we have a vertex going from Water Company to Resident 3. We can call that W3. So we got gas and water going to each resident without crossing. And we can get electricity going from the power company to resident 3. So we have vertex E3. And can I get electricity going from the power company to resident 2? I sure can. Here's my power cable. And this is an edge going from vertex E to vertex 2. Now, I want to get a vertex to go from electric company to resident 1 without crossing any of the other lines. And I'll tell you what I see here. If I follow this line to here, and then to here, and then to here, and all the way back to the power company, I have a circle that completely surrounds resident 1. It doesn't look like the way I've drawn things I can get from the power company to resident 1 without crossing one of these other lines. I don't know. What do you think? Maybe I could have made more clever choices as to how I laid out the lines. We're not going to get service from all 3 utilities to all 3 residents without the lines crossing the way I've drawn it. And it turns out that we can prove using graph theory that this is the best we can do. We got 8 lines, and I'll let this be my set of edges. We got 8 edges from the utilities to the residents. We needed 9. We needed 3 lines from each utility going to the residents. We were unable to get a line going from E to 1 without crossing these other lines. So in other words, we couldn't draw an edge from E to 1 without crossing some other edge. This was a classic brain teaser in recreational mathematics and perhaps also in graph theory at one time. It's a classic riddle. I think one thing that I'll keep from this is that from now on, I won't say we'll always do this, but from now on, very often, we will determine an edge by mentioning the two endpoints of the edge. G1, that's the edge that goes from vertex G to vertex 1. W3, that's the edge that goes from vertex W to vertex 3, and so forth and so on. We looked at this graph before, but we called the edges V1, V2, V3, V4, V5. We called the vertices V1, V2, V3, V4, V5. And we called the edges E1, E2, E3, E4. Here, we've named the vertices A, B, C, D, E. And we've named the edges according to the vertices that they join together. AB is an edge. AE is an edge. AC is an edge. And could we have called this edge CA? Could we have called this edge DA? Yes. Right. We're not really concerned at this point about the direction that we go when we're traveling along an edge. So this edge we could call AB, we could also call it BA. Now we'll introduce the concept of the degree of a vertex. And this is kind of tricky. We're going to define it this way. The degree of a vertex is the number of edges which begin or end at that vertex. We're going to have to clarify one case in a little bit. We don't need to do that right now. But let's look at our example. The degree of vertex A, let's see, how many edges do we have that begin or end at that vertex? 1, edge AC, 2, edge AE, 3, edge AB. The degree of vertex A is 3. And what about the degree of vertex B? We have edge BD, which leaves vertex B. We have edge DE, which leaves vertex B. And we have edge AB, which leaves vertex B. So the degree of B is 3. Okay, what about degree of vertex C? We have the edge CD, which comes or leaves vertex C. We have the edge CE, which comes into or leaves vertex C. We have the edge AE, which comes into or leaves vertex C. So again, the degree is 3. The degree of vertex D, pretty much the same. We have edge CD that comes into D. We have edge BD that comes into D. and we have edge ED, which comes into D. Well, this is getting monotonous, isn't it? The degree of vertex D is 3. Well, let's break up the monotony. What about vertex E? Here we have 1, 2, 3, 4 edges that either leave or begin at vertex E. AE, BE, ED, CE. The degree of vertex E is 4. Now, you might remember a minute ago I said this is how we have to define the degree of a vertex, but this will require some clarification, and I think now is a good time to clarify one matter concerning the degree of a vertex. Here's the clarification that we have to make when we define the degree of a vertex, and it's an exception to the rule. If we add a loop to a vertex, the number of degrees increases by 2. Now, the loop is just one edge, so if we add a loop to a vertex, we think, well, we're only adding one edge, the degree should increase by 1. But I guess for reasons that prove beneficial if we do advanced study in graph theory, it was decided that if we add a loop to a vertex, the number of degrees increases by 2. And let's just look at our last example. Vertex A, 1, 2, 3, it has degree 3. From our last example, remember, it had edge AB leaving A, edge AE, leaving vertex A, edge AC leaving vertex A. The degree of A is 3. What happens if I do this? I add a loop to vertex A. This is another edge that I'm adding, but because it's a loop, the number of degrees is going to increase by 2. So the degree is 5 now. And suppose I do this. I added another loop. This loop is just one edge, but we're counting both ends of the loop as contributing a degree to vertex A. So now the degree of vertex A increases by 2. The degree of vertex A is 7. Here's a nice exercise. We have a map of the southeastern United States, sort of. I guess this shows the limitations of my artistic ability. But anyway, if you use your imagination, I think you can see that this is a map of the southeastern United States. And our exercise tells us to construct a graph in which each of the 9 southeastern states are represented by vertices. So Arkansas will be represented by a vertex, Tennessee will be represented by a vertex, North Carolina will be represented by a vertex, and so on. And 2 vertices will be joined by an edge exactly when the states represented by the vertices share a common border. Tennessee and Alabama share a common border. So the vertices representing Tennessee and Alabama will be joined by an edge. Tennessee and Florida do not share a common border. So the vertices representing Tennessee and Florida will not be joined together by an edge. You know, this seems like the kind of exercise that a person would think of after they've been doing LSD or something like that. But you know, this kind of exercise, I shouldn't call it an exercise. Oh yeah, this kind of exercise is also an application which is used all the time in map making. In map making, maps like this are represented by graphs, vertices, and edges to determine what colors the states should be colored so that no two adjoining states are colored by the same color. So this is, it seems like a bizarre application. And yet, it's a very practical application, believe it or not. And you can believe it because I told you so. Here's what I did. I decided to arrange the vertices going left to right in pretty much the same order that the states appear in the map. Starting up top and going from west to east, we have Arkansas, Tennessee, North Carolina. So here are our vertices for Arkansas, Tennessee, North Carolina. We go down a little bit from west to east, and we have Louisiana, Mississippi, Alabama, Georgia, South Carolina. Louisiana, Mississippi, Alabama, Georgia, South Carolina. And then way down here, all by its lonesome self, we have Florida. So those are the vertices of our graph. And two vertices will be joined together exactly when the states that they represent share a common border. Let's start over here with Arkansas. Arkansas shares a border with Tennessee, Mississippi, and Louisiana. Arkansas to Tennessee, Arkansas to Mississippi, Arkansas to Louisiana. Okay, let's look at Tennessee. Tennessee shares a border with Arkansas. We got that. Tennessee shares a border with Mississippi. We got to put that in. Tennessee shares a border with Alabama. We got to put that in. And Tennessee shares a little bit of a border with Georgia. So we got to put that in. And Tennessee shares a border with North Carolina. Let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yep. Tennessee borders on 5 states. Now, North Carolina borders with Tennessee. We got that. North Carolina borders with Georgia. We got to put that in. And North Carolina borders with South Carolina. Okay. Now, let's do South Carolina and work from east to west. South Carolina borders with North Carolina. We got that. South Carolina borders with Georgia. We got to put that one in. And that's it for South Carolina. Let's do Georgia. Georgia borders with Tennessee. We got that. Georgia borders with North Carolina. We got that. Georgia borders with South Carolina. We got that. Georgia borders with Florida. We don't have that yet, so we're going to have to add that. Here's Georgia bordering Florida. And Georgia borders Alabama. We got to put that in too. Okay, now it's Alabama's turn. Alabama borders Georgia. Let's see. Oh my goodness, where do I want to start? Let's start with Tennessee, okay? Alabama borders Tennessee. We got that. Alabama does not border North Carolina. Alabama does border Georgia. We got that. Alabama does border Florida. We got to add that. Here's Alabama joining Florida. And Alabama joins Mississippi. We got to put that in. Here's Alabama joining Mississippi. And then we get back to Tennessee, so that accounts for Alabama. And just to make sure, let's see, how many states does Alabama border with? 1, 2, 3, 4. How many edges do we have connected to Alabama? 1, 2, 3, 4. I think we got them all. Let's do Mississippi. Mississippi borders, we'll start with Alabama. Mississippi borders with Alabama. We got that. Mississippi borders with Louisiana. We got to put that in. Mississippi borders with Arkansas. We've already got that. Mississippi borders with Tennessee. We've got that. And let's see. How many states does Mississippi border? 1, 2, 3, 4. And we have 4 edges connected to the vertex from Mississippi. We got them all. Louisiana borders Mississippi and Arkansas, and we've got those already. So what we have here is a graph that shows which states border which other states in the southeast. Every vertex represents a state, and every state is represented by a vertex. And 2 vertices are connected to one another by an edge exactly when the states that they represent share a common border. For example, Louisiana and Mississippi are connected by a vertex. Louisiana and Mississippi are connected by a vertex. That's because Louisiana and Mississippi share a common border. Believe it or not, this is an application that is in wide use. Let's milk this example for all it's worth. We'll keep the graph that we drew. We've erased the map of the southeastern United States, but we've kept its graph. In the previous example, the degree of the vertex Florida, well, unless we have a loop, that's just going to be the number of edges coming in or going out, right? So we have this edge and that edge. Degree of Florida is 2. What about Alabama? The degree of Alabama, the vertex Alabama, is the number of edges going in or coming out. We have 1, 2, 3, 4. Degree of Alabama is 4. And that means that Alabama borders on 4 states. The degree of Tennessee Here's the vertex for Tennessee, and we have 1, 2, 3, 4, 5 edges going in or coming out of Tennessee. And what that tells us is that there are 5 states on which Tennessee borders. Tennessee shares a common border with 5 different states in the southeast. Another concept that we want to introduce is that of being adjacent. 2 vertices are adjacent if they have an edge in common. Let's look at Arkansas. Arkansas shares an edge with Louisiana. So Arkansas is adjacent with Louisiana. Arkansas shares an edge with Mississippi. Arkansas shares an edge with Tennessee. What about Alabama? Does Arkansas share an edge with Alabama? Is there an edge that goes directly from Vertex Arkansas to Vertex Alabama without going through some other vertex? No. So it looks like Arkansas is adjacent to 3 vertices. Arkansas is adjacent to Louisiana. Arkansas is adjacent to Mississippi. Arkansas is adjacent to Tennessee. Let's look at Louisiana. Louisiana shares a common edge with Arkansas. So those 2 are adjacent. Louisiana also shares a common edge with Mississippi. And Louisiana does not have any other edges. Louisiana has 2 edges. It's going to be adjacent to the states that those edges are connected to, Arkansas and Mississippi. That's it for Louisiana. What about Mississippi? Mississippi shares a common edge with Louisiana. Mississippi shares a common edge with Alabama. Mississippi shares a common edge with Tennessee. And Mississippi shares a common edge with Arkansas. Now that we know what adjacent vertices are, we can talk about paths. A path is a graph in which the vertices are ordered. So there's a first vertex, a second vertex. They come in a specific order. The vertices are ordered, and each vertex after the first is adjacent to its predecessor. And as an example, we have the path with vertices Louisiana, Arkansas, Tennessee, and Georgia. And since we call this a path, the vertices occur in this order. So we start at Louisiana, and we go to Arkansas. Is Arkansas adjacent to its predecessor? It sure is. They share a common edge. From Arkansas, we go to Tennessee. Is Tennessee adjacent to its predecessor, Arkansas? It sure is. It's joined by an edge. And from Tennessee, we go to Georgia. Whoops. Pay no attention to that man behind the curtain. From Tennessee, we go to Georgia. Whoops. And was Georgia adjacent to Tennessee? Yep, they're joined by this red edge right here. So this is indeed a path. Let's look at another path for the sake of example. Let's see, we'll go Florida, Alabama, Georgia, South Carolina. Florida, Alabama, Georgia, South Carolina. We start in Florida. That's the first vertex, and we go to Alabama, the second vertex. And were these two adjacent? Absolutely. They're joined by a vertex, joined by an edge. Then we go from Alabama to Georgia. Are these two adjacent? Yep, they're joined by an edge. And then we go from Georgia to South Carolina. Are they adjacent? Yep, they're joined by this edge. So the path Florida, Alabama, Georgia, South Carolina is this blue succession of vertices and edges. The path Louisiana, Arkansas, Tennessee, Georgia is this blue succession of vertices and edges. Let's look at a few more examples. And let's consider the path Louisiana, Arkansas, Alabama, Georgia. So we start at Louisiana and we go to Arkansas. And Arkansas is indeed adjacent to Louisiana. Then from Arkansas, we go to Alabama. Is Arkansas adjacent to Alabama? Here's Arkansas. Here's Alabama. Do they have an edge in common? They don't. So you know what we do? We say that these are not adjacent. And we say not a path. Let's do some more. Let's consider the path Louisiana, Arkansas, Tennessee, Mississippi, Louisiana. Louisiana and Arkansas, are they adjacent? They are indeed. Arkansas is adjacent to its predecessor, Louisiana. So here's the first leg of our path. Then we go from Arkansas to Tennessee. Is Tennessee adjacent to its predecessor, Arkansas? It sure is. And Tennessee to Mississippi, is Tennessee adjacent to Mississippi? Yep. Mississippi is adjacent to its predecessor, Tennessee. Sure enough. And Mississippi to Louisiana, is Louisiana adjacent to its predecessor, Mississippi? It sure is. And son of a gun, we have a closed path here. We started at Louisiana, We went around the path and ended up at Louisiana. And this is a special kind of path. A circuit is a path that begins and ends at the same vertex. And in our previous example, the path Louisiana, Arkansas, Tennessee, Mississippi, Louisiana was a circuit. That we started at Louisiana, we ended at Louisiana. And when we drew it out in blue, that circuit essentially was a closed path. This is a nice example. Notice, first of all, our graph A, B, C, D. And E. E is connected to every other vertex. And this says, in the graph, this one, draw the path A, B, E, C, D, E, A. Well, let's see if we can do this. A and B, are they adjacent? Yep. B and E, are they adjacent? Yep. E and C, yeah, they're adjacent. I'm sorry. Yeah, E and C adjacent. C and D, yeah, they're adjacent. D and E, yeah, they're adjacent. E and A, yeah, they're adjacent. So after the first vertex, every vertex is adjacent to the vertex before it. This should be a path. We start at A and we go to B, and then from B we go to E, and then from E we go to C, and from C we go to D, and then from D we go to E, and from E we go to A. Now wait a minute. This path crisscrossed right here at E. Can we do that? Can a path crisscross itself at a vertex? Yeah, it can. So the fact that we have the path going into vertex E and coming out and going to C, and then later on we have the path coming into vertex E and going to A, does not in any way disqualify this from being a path. So we sketched the path, and is there something else that we notice about the path? Yeah, the path is a circuit also. The path begins and it ends at the same vertex. So it is a circuit. The fact that the path crisscrossed itself right here at E does not disqualify it from being a path, and it doesn't disqualify it from being a circuit either. Okay, now we have to talk about connectedness. That's an important topic in graph theory. A graph is connected exactly when there exists a path from each vertex to every other vertex. In other words, pick any two distinct vertices. Is there a path from one to the other? If there is, the graph is connected. If the graph is connected, we can pick any two distinct vertices, and there will be a path from that vertex to the other vertex. What about this first graph here? Oh my goodness, this is about as connected as a graph can possibly be. Pick two vertices, A and D. Okay, here's our path. They're connected. There's another path from A to D. We could go from A to B and B to D. C to D. Well, of course, C and D are connected directly by an edge. Any two vertices here, there's a path going from one to the other. What about this? Is this connected? Absolutely. Well, first note that E is connected to every other vertex. There's a path from E to every other vertex in this graph. So there's a path from E to every other vertex in this graph. Any other vertex, to get from A to B, go from A to E first and then to B. And that's what we do for all of the other vertices. A and C, go from A to E first and then from E to C. D and B, go from D to E first and then go to B. What about this one? Not connected. Why? There's no path from B to the vertices C, D, or E. There's no path from A to the vertices C, D, and E. So this is not connected. See, one more little tidbit and we are done. Let me clarify something that I said just a second ago. I said this graph was not connected, and that's true. But there's a special term for a graph that's not connected. And we would actually say disconnected. So as far as graphs go, a graph is either connected or it's disconnected. This graph is disconnected because there's no path from A to C, there's no path from A to E, and so forth. The fact that there is a path from C to E or C to D makes no difference. If there's even one vertex that's not connected to every other vertex, we say the graph is disconnected. So a graph is disconnected if it's not connected. If it's connected, every vertex has a path going from itself to every other vertex. If we don't have a path going from every vertex to every other vertex, the graph is disconnected. So a graph is disconnected if there's not a path from every vertex to every other vertex. And here, there's not a path going from vertex A to C or a path going from vertex A to B. There's not a path going from vertex B to vertex E and so forth. This graph is disconnected. This is our last topic, a bridge. An edge of a connected graph is a bridge if removal of the edge makes the graph disconnected. First of all, note that we can only have a bridge if we have a connected graph. If the graph is not connected, then there can't be a bridge. So if we have a connected graph, an edge in that connected graph is a bridge if removal of the edge makes that graph disconnected. And let's look at this example. Same example, I'm just going to remove the paths that we drew from before. Now I claim here, first of all, the graph is connected. But I claim that every edge of this connected graph is a bridge. Every edge is a bridge. Why? Let's say I remove this. If I remove that edge, there's no path from A to any other vertex in the graph. So this edge is a bridge. If I remove this edge, there's no path from A to any other vertex in the graph. If I move this edge, there's no path from B to every other vertex in the graph. So this edge is a bridge. Similarly, if I remove this edge, there's no path from C to every other vertex in the graph. So this edge is a bridge. If I remove this edge, there's no path from D to every other bridge in the graph. So every edge in this graph is a bridge. What about this graph? I say there can't be any bridges because the graph's not connected. Remember, we only find a bridge in a connected graph. So if we don't have a connected graph, we can't have a bridge. Now, what about this graph? If I remove this edge, I can still get from A to E to B. I can still get to A to C. I can still get to D from A. So this edge is not a bridge. And the same logic applies to all of these other edges on the outside. What if I take away, well, let's see. Did I just say remove this bridge? I can't remember. Remove this edge. If I remove this edge, I can get from A to B, from A to B to E, from A to B to D, from A to C. This edge isn't a bridge. I can still get from A to every other vertex. And the same logic applies to all of these other lines on the inside, or all of these other edges on the inside. What if I remove that edge? Well, A is still connected to every other vertex. I can get from A to E to B. So I can still get from A to B. I can get from A to C. I can get from A to E. I can get from A to E to D. A is still connected to every other vertex in the graph. There's a path from A to every other vertex in the graph. So the graph is still connected. There is no edge in this graph that is a bridge. Maybe we'll look at one more. Let's see. This is a connected graph. I can get from B to A to E to D to C. I can get from any vertex to any other vertex through a path. So this is connected. So we might have bridges in this graph. Is this edge a bridge? If I remove it, I can still get from B to A to E to D to C. I can still get from A to E to D to C. I can still get from E to D to C. I can still get from D to C, and vice versa. If I remove this edge, I can still get from any vertex to C and vice versa. So this edge is not a bridge. And by the same logic, this edge won't be a bridge. What about this edge? I can still get from E to C and E to D. And from A and B, I can still get from A to E. I can still get from B to A to E. And from E, I can get to C. I can get to D. The graph is still connected if I remove this edge. So that's not a bridge. What if I remove this edge? Whoops. No way to get from A or B to E, C, or D. So this edge is definitely a bridge. AE is a bridge, that edge. Do we have any others? What if I did this? Whoops. Now I can't get from B to any other point on any other vertex of the graph. So this edge was a bridge also. I removed the edge from A to B, and the graph is no longer connected. So A to E was a bridge, and A to B was a bridge also. So we have two bridges in this graph, AB and edge AE.